Good afternoon, Year 12. Hello. Thank you very much for joining me. Going to be looking at paper 3 today. Nice to see that everyone's saying hi on the chat, so I can do the register. Who's Xavier Sword? I don't know who that is. So I've got Dana, Ria, Ivan, Sherlyn, Nikita, Xavier Sword, who I've got no idea who it is. Emma, Julian, Tenzi, Dan, and Julian. Whoa, you switched accounts. Who did? Oh, it's Tenzi. Oh, Tenzi switched accounts. Okay, cool. I like it. Fab. I'll put you on the register. I've got Dat. Anyone seen Jasmine or Kayun or Ben? Got Tenzi. Got Sherlyn. Got Emma. Got Nikita. Got Ivan. Anyone seen Mika? Still missing a few people. How's everyone doing? How's everyone coping with their lockdown? I hope everyone's well and safe. I guess what I'll do is, since this paper is going to be a tight fit to get into the lesson, like a really tight fit. Karen, hello. I've got to try and do this whole paper in under an hour. Jasmine, hi. Thank you so much for coming. That's great. Doing really well. We're only missing Ben and Mika. If anybody could send them a message, that'd be super handy. I'd really appreciate it. Right, guys, let's crack on with paper 3 today. I've already noticed that Dat has put up his data. He's the only one to have put up his data. Year 12, I need your data. Please put your data in. Dat also mentioned that the mark scheme for paper 3 is missing an answer for question 4CII. So I'll have a go at trying to fill in that gap. Right, let's crack on, folks. Share screen. Let's get her moving. Let's do that one. Hide and straight into the paper. Right, so just a quick confirmation. Can I just check with somebody? I don't mind who lets me know. Is this the correct paper? The mark scheme is incomplete. Okay. Is this the correct paper? Question 1 being a flame test. Is this the right one? I just want to check because apparently I was looking at an A2 paper and it turned out for the first 5 minutes I was doing the wrong one. I thought it was very entertaining. Fab, that's great. Thanks, guys. Appreciate the feedback. I'm going to ask for a favor from Emma. Emma, can you do me a solid? Can you do me a favor? Can you just keep track of the times? Just keep a note, a little piece of paper note of whenever I change question. So question 1, 2, 3, and then the time so I can time stamp this later on. Thank you so much, Emma. You are a star. Okay. So question number 1, a white compound. A white compound is a group 2 metal ion. Sorry, I've just got bits on the floor and I've just trodden on them. Not entirely sure what it is. Group 2 metal ion and an ion and water crystallization. So we have got a group 2 metal, a Gr2, and it'll be a +2, of course, metal, 1 anion, and dot XH2O. So we've got waters in this because it's got a water crystallization. And it gives us a red flame test. And yes, you have more flame tests to learn than you did at GCSE. There's only one group 2 that does a red flame, folks, and that is strontium. And it says, describe how you'd carry out a flame test. Okay, so you had 2 methods at GCSE, one with a wet splint and one with a nichrome wire. The wet splint is now dead. So we have to now focus on using the nichrome wire. So we're going to use using nichrome wire. By the way, follow-up questions. Why nichrome wire? It is inert. It is inert and has a high melting point, high MPT. Common questions. Using nichrome wire, wash wire in hydrochloric acid. Eek! I'm ahead of myself. Hydrochloric acid wash in hydrochloric acid. That removes any contamination, any previous test, removes previous tests, previous test material, and then we're going to pick up sample, pick up solid sample, and place into roaring. You've got to say that. You're probably allowed to say blue, or probably allowed to say blue flame. Place into roaring Bunsen burner flame. I'm actually going to put Bunsen burner flame. I am actually going to write down next to that, because sometimes I've seen them do odd things. I'm just going to put blue flame. Yeah, just to clarify that. The reason why is if you use a yellow flame, if you use a luminous flame, which is the yellow flame, the yellow masks the flame color. Yellow masks color. So you can't see it properly. Ambiguous results. Next, identify the ion. So this is strontium. I'm going to do it by name. Strontium. But make sure you've got to remember it's the ion. I think if you forget that, strontium 2+. Brackets Sr plus 2. They are the formula as well, so it's nice to give both. W dissolves readily in distilled water to form a solution. Okay. Describe what you would see if some dilute sulfuric acid were added. Ah, really lovely question on solubility. Yeah, you'll remember. So if some dilute hydrochloric acid was added to our mixture, and what's going to happen is we're going to form a group 2 sulfate. We're going to form strontium sulfate, which is insoluble. We remember the solubility rules. So group 2, beryllium, magnesium 2+, Mg 2+. Then we've got calcium 2+. Now it's big enough that I can fit it in it. Then we've got strontium 2+ and barium 2+. Yeah, anything below here is pretty much insoluble. So these are all going to form white precipitates. So what we're going to see, we're going to see a white and I'm actually going to write precipitate because it's an exam, precipitate instead of PPT. White precipitate forms. Do they ask us to identify it? No. Right ionic, there you go, right ionic equation for its formation. Sr2+ plus SO4 2- going to SrSO4. States with state symbols. So that was aqueous, that was aqueous, and now that one's solid. And we're done. Nice, easy start. Okay, when W is heated, so we know we've got strontium 2+ in here. Yeah, when it is heated, a colorless solution forms. Ooh, that's entertaining. They're driving out the water. That's really interesting. That's rather a bizarre observation, by the way. The reason being is most people would expect the solid to continue to dry out, but instead it becomes a liquid. It's not becoming a liquid, it's dissolving into the water that's crystallized in the solid. At the higher temperature, it's soluble in that quantity of water. So it'll start to form like it won't look like a color solution. It looks like a white sludge in reality, just so you know. As heating continues, droplets of X appear and they condense at the top of the tube. White solid remains. Okay, on further heating, Y melts and a brown gas is given off. A glowing splint is held and relights. Okay, when heating is finished, a white solid Z is left in the test tube, identified by name or formula, X, Y, Z, and the two gases. Okay, so X droplets, that's going to be water. Yeah, that's the water of crystallization being driven out. That's then condensing at the top of the test tube. We would actually do that practical, by the way. We can totally do this. This whole thing is totally doable. A white solid remains. That's going to be, I don't know who that is yet, but Y melts and a brown gas. The brown gas is nitrogen dioxide, and the gas that relights a glowing splint is oxygen. Are we allowed to do formulae? Yeah. That means Y was strontium nitrate. Strontium nitrate. That's where the NO2 comes from. It's actually hydrated. Oh, is it hydrated strontium nitrate? No, white remains in the test tube, so it's not hydrated. I bet they'll penalize for that. Do watch out. Z being left behind in the back is going to be strontium oxide. Strontium oxide. So what's happening is a two-step process. The hydrated strontium nitrate, Correct formula, of course, SR is a 2+, nitrate 1-. That was a .XH2O. They heated it. They drove off the water to form anhydrous strontium nitrate, and then they heated it again, and then they had it decompose to give strontium oxide, NO2 and O2, and that probably balances 6. No, not quite actually. 6, it's the oxygens that don't add up. All the nitrogens. Oh, got to balance for the nitrogens. Yeah, that's going to put me over on the oxygens now. So 1, 2, 3, 4, 5, 6. That's going to be half a mole of oxygen. There we go. There's the equation for that. Quite nice to do. Next, a sample of W is heated until only solid Z is left. Okay. Describe how we check that the reaction is complete. No more brown gas produced. No. Oh, first one, no more brown gas produced. That I can't. No more brown gas released. That's the first one where I'm like, oh, that's not very nice. Don't like that very much. Right. Okay. Calculate the empirical. So W contains. Oh, calculate the formula of W given that 0 of W has a mass of Z. Mass. Oh. So the question is, who am I? Hang on a sec. Okay. Calculate the formula of W given that this many moles of W with the mass of gave that many moles of Z. Z is strontium oxide. Okay. So SR. Ooh, that's interesting. I'm just going to give the formula, folks. Of W of Z, right? So we're going to have S. Oh, okay, folks. It's a bit more tricky, this, isn't it? SR of W. What was W? W was the full thing. Okay, with the water. .XH2O. I had 0.01 moles. That's interesting. Moles of that guy. I'm going to heat it to form SR with Z. Z is strontium oxide. Oh, blimey. SRO. Calculate the formula. How fascinating. So we're going to get everything. We're going to get water. We're going to get NO2. We're going to get O2. Right. And that strontium oxide is Z. And W is the full thing. How bizarre. Right, okay. So I've got 1.036 grams of that guy. Grams over rams, calculator. Need to turn it into moles. Can't do empirical without moles. They haven't given us any information about the water or anything, which is fascinating. But we can certainly balance for it. We're going to need 2 nitrogen dioxides and a half an oxygen. And then we can just leave that as X in there, like that. But we're going to have an... Oh, okay, anyway. So, strontium, no idea. That's a hard question, folks. That's a bit of a nightmare. Strontium, down there. 87.6. So, 87.6 plus 16. But I'm going to lose my mark, aren't I, for that, folks? 87.6 plus 16 gives me that. I'm going to lose my mark for that. There's a mark for 103.6. Oh, look at the number. I know that's right. Oh, the mole is already given. No, but it's not for that guy. Oh, it is already given. You're absolutely right. Moles and moles. You're absolutely right. Yeah, so it's the same, 0.0, I'm an idiot. Right, so at that point, are they asking us to flip back to mass? We can work out the number of, so okay, so NO2 is going to be double that. O2 is going to be half that. Blimey. Right, turn it back into mass. I'm trying to find out the water, folks. That's what I'm trying to do here. Trying to find out the water. Yeah. So And you're right, they've already given me the mass. That was 2.836 grams. I'm going to need that in a minute. NO2 is 14 plus 16 plus 16, 46.0 for that. So times that by 46.0, times that by 32. So 0.02 times by 46. Wow, that slowed me down somewhat, hasn't it? And then 0.005 multiplied by 32 gives me 0.16 grams. Right, now, no need to calculate, you're absolutely right. Now I can work out the total. I can work out the total mass here, therefore the mass of water. 1.036 plus 0.92 plus 0.16 gives me equals 0.036, 1.036, sorry, plus 0.92 plus 0.16 gives me a total mass of 2.116 grams. Right, now I can work out the amount of water. So 2.836 minus 2.116 equals 2.836 minus answer gives me 0.72 grams of H2O. Turn it into moles, grams over rams over 18. Divided by 18, it's speeding up now at this point, 0.04. And look, that number there with air, that number there is 4 times bigger than that number there. So X is 4. So the final answer, that's really hard. NO3, close brackets 2.4 H2Os. Blimey, end of question 1. Eek. Want to mark that. Have I got anything wrong so far, folks? I feel like I want you guys to give me the feedback on it. Have I got anything wrong so far? Ooh. Anyway, I just realizing that I don't have an awful lot of time here and I need to crack on. Question number 2. So I've been doing this for 16 minutes already. Question number 2 is about finding the identity of 2 organic liquids P and Q, which have the same functional group. P and Q are isomers containing carbon, hydrogen, and oxygen only. When phosphorus pentachloride, I haven't got anything wrong, Dat. Thanks. I think that's a good answer. Good. Phosphorus 5 chloride is added, so we're testing for an alcohol. That's the test for an OH group. A gas is given off. That gas is going to be HCl. Identify name or formula. HCl gas. Keep it short for myself. Yeah, by the way, if you choose name, you can't write hydrochloric acid. It's not the correct answer. The answer is hydrogen chloride. There's no water present here. Give a possible reason why the gas forms steamy fumes when mixed with moist air. HCl is very soluble in water and causes droplets to form when HCl dissolves. Eek, that's also tricky. That's what I would write. Don't know if I'm going to get the mark for that. It is very soluble. It does form droplets, and it's when the HCl dissolve. The HCl molecules act like a nucleation site for bubbles. It allows the water droplets to kind of be pulled together, and it forms in the atmosphere. So you get to see them form like clouds. A few drops of acidified potassium dichromate are added to separate samples of P and Q. This actually is further solidifying my concept of it being an alcohol. Identify the functional group in P and Q. OH minus. I'm going to put alcohol group. It doesn't say, it just says identify, so you can give it by word or by name or by formula. So alcohol, brackets, OH. Give the formula of the ion responsible for the green color. We know that acidified potassium dichromate is one of my favorite substances. It's highlighter orange. And the highlighter orange has chromium in a +6 state, but it turns green because it becomes chromium 3+. So give the formulae, notice it's in bold. So chromium 3+ is my answer. At A2, by the way, it would be Cr brackets H2O. This is it at A2. This is the AS answer. At the A2 answer, it is this. It is actually the hexaaqua chromium 3 ion. State 2 possible observations you would make when a small piece of sodium is added to either both fizzing. State 2 observations. Ooh, it'll fizz. Oh, fizzing will occur. And the metal will float, but the alcohol's less dense than water, so it doesn't always float. So I don't trust it. Fizzing will occur, and the metal will disappear. Metal will dissolve. Will disappear. Blimey. Next. The mass spectrum of P and Q both have a molecular ion at 60. Okay, so I know I'm going to be able to put a number of carbons on this now, isn't it? The mass spectrum also has a peak at 31, which is not present in Q. God. Right, okay. So we know it has an alcohol group. Well, that's 16 plus 1. How do I get to 60? Methanol's way too... I know that ethanol's 46. It's one of my best chatted lines ever. Yeah, can I buy you a drink with an MR 46? So it's bigger than ethanol. Let's go for propanol. 12 plus 12 plus 12 plus 16 plus how many hydrogens? 1, 2, 3, 4, 5, 6, 7, 8 plus 8. 60. Okay, so it's prop. It's got 3 carbons. Yeah. But then the mass spectrum of P has a peak at 31. That's interesting. Give the formula for the ion responsible. C3H7OH. I absolutely hate that. I'm not doing it. I refuse. CH3, CH2, CH3 plus structural formula, proper chemistry. What the heck is the one at 31? I'm even going to put the charge on the correct atom. I just got that wrong, haven't I? Oh, 60. 60. Ah! I made a mistake. It's okay. It's all right. Yeah, plus. There we go. There's that guy. And then 31. God, chop this up. Well, we know that this group here is 15. That one there is 29. What's 30? Oh, 31. It's the other half. There it is. So that's going to be CH2OH plus. That should give me 29. 12 plus 2 plus 16 plus 1. 31. Whoop, whoop. There we go. Like it. Right. Give the structures of the two. Well, there's only 2 alcohols with propanol. Yeah, there's either propan 1-ol or propan 2-ol. And which one had the peak? Which one had the chop there? Because that would be propan 1-ol. P also has a peak. So P is going to be propan 1-ol. And that's because you can fragment it, yeah, and produce a peak at 31. Fragment it there. So there's the structural formula of P, and Q then is going to be propan 2-ol. I'm going to put the OH down just to give myself a bit more space between the 2 molecules. There we go. It's actually asking me, by the way, just so you know, it's asked me for structural, not displayed. Easy to make that mistake. CH3, CH2, CH2OH. And then this one is CH3, CH, open brackets, OH, CH3. Yeah, so I've given displayed and structural. They're not going to penalize me. They won't care. Next. Question 2 down. Next. Holy moly. What is that? This question is about determining enthalpy change of hydration of sodium thiosulfate. Oh, by the way, that's borderline. So they're going to make a saturated solution and then let it solidify. God, the amount of problems you'd have with that is massive. This enthalpy change cannot be measured directly. Oh, okay. No, you're right, it can't. That is impossible because it dissolves. Yeah. The enthalpy change when naught of anhydrous is dissolved in water to form 1 molar solution is determined. This is carried out using an electrical compensation calorimeter. Blimey. That's saying that they're compensating for the heat loss. Blimey. The addition of anhydrous thiosulfate causes the temperature to rise by 3 degrees. That's tiny. The temperature is allowed to fall back to the starting value. The supply switched on and the joule meter is used to measure the energy change required to produce the same temperature rise. In this experiment, 1,260 joules was needed. Blimey. Give 2 advantages of using electrical compensation condensation calorimeter compared to a polystyrene cup? Okay, first one is you're going to reduce heat loss. Obviously, obvs. What would the second one be? Less splashing. Yeah, that's really interesting. Electrical heater. Less splashing seems a bit vague, that, but a polystyrene cup. Polystyrene cups are quite flimsy, yet you could potentially damage the polystyrene cup. What other ones would I choose there? Reduces heat loss. Then a polystyrene cup. This has a lid. No, but that's heat loss again. Less chance of splashing. Wow, I feel like I am reaching there, folks. I am reaching. I feel like it's because it's compensating. It's going to reduce heat loss and then compensate, and it just says give 2. So if I give 2, I need to give my top 2. Ooh. Electrical compensator. The polystyrene cup is oh, I don't know. Compensates for heat loss. Electrical compensates. I'm just going to write that down. Yeah, I've reached. I'm going to lose one. I know I am, folks. Compensates for heat loss digitally. Oh, sorry. I'm an idiot. It's more accurate. More accurate. Oh, darn it. That's going to be the right answer. It's going to measure the temperature change. More accurately measured temperature change. That's what it's going to be. More accurately measured temp change. Holy moly. That's my choice. What a nightmare. What a nightmare. No idea if that's right. In the experiment, this requires to raise the temperature, calculate the enthalpy change for 1 mole of anhydrous. Wait. Okay. How much did they use? The enthalpy change when 0.1 is dissolved in water to form a 1 molar dm cubed solution. Ooh, isn't that interesting? For dissolving 1 mole to form a 1 mole per dm cubed solution. Enthalpy change. Oh, they're doing a clever trick. It is wrong. No! Spoilers, dude. Oh, I got it wrong. I knew I was going to get it wrong. Oh, it sucks. I hate it. The anhydrous sulfate. Hang on a minute. You're forming the same solution. The enthalpy, the sign, calculate the enthalpy change of a solution for dissolving 1 mole of, you're going to be dissolving it in a liter. The answer is going to be the same number. That's really clever. Because they're dissolving 0.1 to make a 1 molar, so that more accurate is rejected. Duh! Duh! So frustrated. I so thought I'd clocked it. It's because it's not using a digital thermometer. It's using the same thermometer. Less splashing. Less dangerous, less hazardous. Less likely to damage the... Oh, I don't know. Next. Okay. So Q equals MC delta T. We've already done it. They've already given me the joules. They've already given me Q. Divide by 1,000. Step number 2. So I'm going to do 1.260 kilojoules. Yeah. And then I'm going to go delta H equals Q over N. Right. What's the moles? Oh, it's 1. So I'm going to have 1.26 kilojoules per mole. That's what my answer would be. Clever. I'm actually going to write down up there, by the way. I'm actually going to give my numbers over 1. Yeah, definitely. There you go. I'm actually going to sub that in like that. The experiment is repeated with 0.1 moles of hydrated. By the way, I'm very aware that you guys have told me it's wrong, and it has massively upset me. It has. You guys are rubbish. I need the mark scheme. Where's the mark scheme for this horrible thing? I don't even know. Hang on a sec. Hang on. I don't have it. CIE, no. EdXL, past papers. I'm just finding the mark scheme, folks. I am devastated that I lost it. Which one is this? This one is October 18, paper 3. October 18. And I'm on an Edexcel. Do I need to be on the international one? I think I do. Yeah, I found it. Right, I found it. Hang on. I want to see what they wanted. What did they want? Did they say any of them? Oh, have I missed a question? Have I missed a question? I missed one. No more brown gas released. Heat until it says it allows it. Allow not brown. Okay, that's fine. Okay, I was down here. I hate you. You horrible question. You horrible, horrible question. Where are you? Okay, allow 2 from no energy lost, much less heat. Okay, next one. Allow energy change can be measured directly. What? No need to consider heat capacity or mass of the solution. No need to consider heat capacity of the solution or of calorimeter. What? That sucks. That sucks, folks. Don't like it. Measured more precisely. Sucks. Right, okay. Next question. So this question, apparently I've got this one wrong as well. Partly because I've forgotten to flip it. I've also got to remember that that number there, that energy, I will make 10 times as much energy. So I need to multiply that by 10 as well, which will give me minus 12.6 kilojoules per mole. It's really hard, easily done. Yeah, that was the energy. Just to explain, that energy there came from us dissolving. That was up here. That was 0.1. I highlighted it there. Yeah, that was 0.1. I'm going to get 10 times as much heat. Yeah, it's going to be the same number, but it's just going to be 10 times larger. Yeah, and then I've just got to remember to flip the sign as well because it's exothermic. I always forget that one, folks, just so you know. Oh, yeah, divided by 1. I got it right. Sorry, yeah, divided by 1, and then times by 10. Next, that's vile. The experiment is repeated with 0.1 moles of sodium thiosulfate. Sodium thiosulfate hydrated using the same electrical compensator to allow for the water crystallization. Slightly less than 100 centimeters cubed of water was added. Calculate the amount of water that should be added. Huh. Wowza. Okay, so we're going to go from Na to S2O3.5H2L. It's hydrated sodium thiosulfate. And we are trying to, I'm sorry, I put that in the wrong place. Yeah, that should be over there. I'm trying to make that by taking sodium thiosulfate, S2O3, add water. The experiment is repeated with of hydrated, using the same electrical, to allow for the water crystallization, slightly less than 100 centimeters of water should be added. Right, so water is 1 gram per centimeter cubed. So if you're doing 0.1 moles, I'm going to make my writing a bit smaller. I've also lost my, lost everybody. There we go. Oh, okay. More accurate is rejected. Why do we divide by 0.1 when the question says 1 mole was used? Oh, wait, never mind. The mark scheme says divide by 0.1. Was that a mistake? I'm confused. No, I've just decided. Oh, Ria, great question. Is that what the mark scheme says? Divide by 0.1. I divided it by 1 because I was like, we're using 1 molar here. But then in order for me to use that, I've got to remember to multiply the energy output by 10. And you realize that 0.1 versus 1 is times by 10. Yeah, we used 1 mole in the second experiment, which is why I divided it by 1. I'm just going about it slightly differently. It wouldn't make any difference in the end anyway. As long as you get to the right answer. I just multiplied it rather than by putting in 0.1 instead, because it didn't make any sense in my head. I prefer to divide by 1 and then realize that that heat will be 10 times bigger. Yeah. So you multiply it up, that's all. Try not to overthink it. They're relatively common. Right, so if we've got 0.1 moles of this guy, yeah, and it tells us the hydrated, yeah, if we've got 0.1 moles of this, we are going to need 5 moles of water. What does 5 moles of water weigh? Yeah, so 5 moles times by 18. Yeah, 5, slightly less. 5 times 8, what? 5 times 8, what am I doing? 5 times 18, 90. Ah, so I only need to add 10. Oh, okay. I have no idea if that's right. That's a horrible question as well. The amount of water that should be added should only be 10. The reason being, the experiment is repeated with hydrated. It's got water in it already. That when that's heated up, the water will be kept inside the thing. It'll like the water will evaporate and condense inside the container. Yeah, it'll condense inside here and return to the vessel. Yeah, if you had a solid in here and you heated it, the water would evaporate because of the heat, but then it's just going to return back in it. So I only need to, so I've got 90 just from the crystal itself, and I now need to add only 10 extra. Ha! Fascinating. What a disgusting question. Ugh. So calculate the amount of water that should, so it says, allow for the slightly less than 100 centimeters cubed water should be added, and that's 90, I'm assuming. Oh, hang on a minute, it's slightly less than 100. Should be added. Calculate the amount of water that should be added. That question itself is foxing me. To allow for the water crystallization, slightly less than 100 centimeters of water should be added. Calculate the amount of water that should be added, 10 centimeters cubed. I have no idea if that's right. What a horrible question. The question is horrible. Slightly less. That's 90% less. What? That's vile. I don't like it at all. It's really mean. Ugh. Am I right? Oh, I don't like having to check the marks game. Oh, that's correct. 10 centimeters cubed. That's evil. It says slightly less than 100. It's 90% less. That's horrible. That's really, really mean, folks. Really mean. That's pure evil. I think that's downright dirty, in fact, just so you know. I think that's really, really mean. Just so you know. Let's go back to there. Right. The enthalpy change determined for this reaction is plus 43. Explain the change in the use of the electrical needed to measure this calorimetry. Well, it's become endothermic. So rather than heating, that's really interesting. So low voltage, an electrical compensator calorimeter consists of a vacuum flask with an electric heater and a thermometer connected to a low voltage power supply and joule meter. So we've gone from exothermic to endothermic. Explain the change in the use of the electrical calorimeter. The change in the experiment was explain the use. How horrible that is. Hang on, sorry, folks. Oh, I see. Can't wait to see if I can answer these questions. Well, that's just flat out mean, isn't it? You guys are mean. Change in the use. Change in the use. The enthalpy change dissolves in the carried out using the electrical compensator consists of a vacuum flask with an electric heater and a thermometer connected to a low voltage power supply. The addition of that causes the temperature to rise by 3 degrees. The temperature is allowed to fall back down. The power supply is switched on and the joule meter. Right, so hang on a minute. So it's heated up and it's then allowing it to cool back down. The power supply is switched on and the joule meter is used to measure the energy change required to produce the same temperature rise. Right. So this is going, how many marks is this? 2. Right. So this is going to be endothermic. We're going to, oh my goodness, switch on calorimeter at the start to supply the heat, the energy required. Oh, they've flipped it. That's what they've done. I know that's what they've done. The temperature is allowed to fall. The power supply is switched on, allowing it is allowed to fall back down. They're going to follow. No, they're going to do exactly the same thing, folks. They're going to switch this on, and because it's going to cause it to drop. Yes. Okay. Switch calorimeter. Switch on calorimeter after temperature. After temp has stopped falling. And measure joules. How did they phrase it? I'm running out of time. Measure and the power supply and the joule meter, and measure joules needed to raise temperature, temp back to starting value. Oh, I have no idea if that is correct. That is one of the most disgusting questions I have seen in ages. Calculate the enthalpy change of hydration of anhydrous sodium sulfate. I know it's going to be wrong. Leave me alone. I did that. Same here. Oh, hang on. Holy moly. Hang on. I've got questions coming in thick and fast, and I seem to have missed them all. How did that happen? I am confused. A question for the Q. The mark scheme says to do 100 centimeters cubed minus 10. Why do they do that? It's 100 minus 9. Wait, I think the answer was 91. I have no idea. Because you want 100 centimeters cubed of water. Why does the mark scheme have two answers? Oh yes, I think 10 centimeters is in the allow bit. There is only 9 centimeters of water in the crystal. Why is there only 9 centimeters of water in the crystal? There's 5 moles. We've got that many moles. It's going to be 90 cent. Oh, because they used 0.1. I'm an idiot. They used 0.1. So it should have been 0.5. I made a mistake. I made another mistake. This paper's horrible. We've got 0.5. Sorry, I just didn't multiply it by the ratio. Times 18 gives me 9. I apologize. Darn it, already made another mistake. So I now need to add 91. Oh! 91 centimeters cubed. I'm an idiot. I'm sorry. I'm a doofus. Ignore me. It's 91. No, it doesn't. You get M1, M2, M3. Second method gives M2. Yeah, M1 is not given. Yeah, that makes sense. Yeah. So asking how much water is added it should be 91, right? Yes. Sorry, you are correct. I made a mistake. What's the next one? Oh, I don't even want to know. This is upsetting me already. I forgot, by the way, you guys saw that I got the moles and I got the ratio of 1 to 5. Yeah, I just had to multiply that by it. I just missed a step. 43 minutes down, guys. Nowhere near am I going to finish this paper in an hour. Calculate the enthalpy change of hydration of how long is this paper meant to be, by the way? I don't actually know. It's meant to be an hour and a half. 1 hour 15. Okay. Next, calculate the enthalpy change of the hydration. Right. Okay. So it has cycle, including the sign. Right. So what did we do? We did that into its solution, that into its ions. I'll just put aqueous, it's easier for my cycle. I don't know if there's a mark for the cycle. Plus H2O, 5 of them, liquid, and then I've got the arrow there as well. So the thiosulfate one, we can now start picking up our values. This is where having this is, so the thio solid plus is minus 12.6. That's minus 12.6. What was the other one? The hydrated was plus 43. That's plus 43. Is it 43 point something? 0.1. Yeah. Hess cycle that way equals that way. So I'm going to go delta H equals with me plus brackets minus 1 minus 12.6 plus brackets plus 43.1. Run that through my calculator. Plus brackets minus 12.6 plus brackets 43.1. That gives me plus 30.5. If you forget that charge sign, you will miss it, kilojoules per mole. That's my answer. Next. I feel like I need to move on if I'm going to finish this, and then we can look at the mark scheme. Check if I'm right, please, folks. Please let me know if I've made a mistake, and then I'll go back and fix it. Although I do want to check to see whether or not it allowed. What did it want me to say? Totally ruined that. The reaction is endothermic. Stroke temperature to decrease. Rather than waiting for the temperature to reach the original temperature, the reaction in the mixture would just have to be heated back to its starting temperature. There is no need to wait for the temperature to fall. Yeah, there you go. So I think I got that one. Did I say endothermic? I said it. Did I write it? I didn't say it. I didn't write it. I would have lost it. I said it, but I didn't write it. Now that's interesting. Plus 30. Please tell me I got the right answer. Oh, what have I done? It's going against me. I am failing at this miserably, folks. This arrow is going against me. I'm an idiot. It is not plus. It is minus. I'm an idiot. I'm sorry, Year 12. I am not doing a good job of this paper. The next one will be better. You realize paper 3s are hard. Brackets minus 12.6 minus brackets plus 43.1. That's a nightmare. I hate this game. I'm not enjoying it at all. Kilojoules per mole. Are you guys even still there? I feel like you've left me. The temperature of the water is measured using a thermometer with an accuracy of this. Calculate the percentage uncertainty for the rise of 3. So plus or minus value. For the measurement of the temperature rise. Well, if you're going to do a rise, that's horrible. The question's a trap. In order to work out a temperature rise, then you'd have to take 2 measurements, so it would double it. I don't care. Of 3 degrees. That's so mean. That's a lie. I don't like it. They don't actually give us the starting readings at any point. I disagree with their chemistry. All right, fine. It's complete garbage, but whatever. 0.1 divided by 3 times 100. 3.3. No, it's rubbish. It's way too high. I'm really struggling here, folks. This is awful. Times by 2. I hate this. This is a nightmare. 6.66. I disagree with all of that, folks, entirely, but whatever. Although it is kind of right, I guess. You do have to take 2 readings. It doesn't really matter because you can't take a thermometer. No, it is correct. I'm not doing this very well. The volume of water used in the first experiment. I'm getting annoyed at this. The volume of water used in the first experiment is 100 centimeters cubed. This is measured with a 100 centimeter measuring cylinder. Reading to the nearest 1 centimeter. Give a reason why, in terms of uncertainty, what the measurement is used rather than a burette. Because the thermometer already has a bigger error than the other one anyway. So it won't matter. It's a tiny error compared to the thermometer. I'm going to calculate it. 1 over 100. Measuring cylinder only has 1 reading as well. Is 1%. Yeah. So that error is much smaller than the 6.6 of the thermometer. Although it would add up. It would accumulate. But the burette will... Oh, you'd have to use a burette twice for a start. Burette only holds 50. You have to take the reading twice. Burette only holds 50. That's what I'd write down. Only holds 50. So would have to refill. Still don't like it. Still don't like it. Obtaining pure dry crystals of an inorganic salt. I'm very aware that, guys, you have another lesson in 5 minutes. I am going to pause this exam review here. End of part 1. I'm very aware that I can't just go as long as I like here. You have other lessons and I will get told off. Right, let's go back to the classroom. Stop screen. Way, we're back. Finished up. Nice one, Ben. What the hell? What? That's interesting. I don't know quite why, but I'm here. It's really strange. Emma, can you send me an email with those questions on it? That'd be great. Wow, question that was long, wasn't it? Question 1 was horrible. Long questions. I wonder how far through I am. How far through are we? Are we nearing the end? Oh, yeah. Oh, we're only 1 question away. Oh, that's irritating. I could have done that in 5 minutes. Both processes start by heat. Obtaining pure dry crystalline organic salt solution is important processes. I feel like I can't finish. I won't do it. I'll pick this up next lesson, folks. I'll finish that off. Guys, I will leave you be for the rest of the day, and I will see you. I just can't remember when I see you next. When do I see you next? Not that matters. I will see you next lesson, and I will finish this off, and then I'm going to start the next paper, folks. Bye, guys. Have a good rest of the day. See you later.